Great. Good afternoon, everyone. Welcome to another Talk Tuesday for iHARP, and I'm very happy to welcome Dr. Christopher Shuman for this talk. Dr. Shuman is a research scientist with the Cryospheric Sciences Laboratory at the NASA Goddard Space Flight Center and also affiliated with UMBC through the Joint Center for Earth Systems Technology. And very happy to also share that Dr. Shuman is also an affiliate with iHARP now. And he has an illustrious background with lots of different missions, but one mission I would mention is the ISAT mission, where he was the deputy project scientist from 2001 to 2005. Dr. Shuman received his PhD and master's in geology from the Penn State University. So with that, Dr. Shuman, it's all yours.
Thanks, everybody, especially on such a beautiful afternoon for staying inside and hearing a little bit about Landsat at 50 years and the Zachariæ Isstrøm project that I'm working on with Mark Fahnestock. And special thanks to all the folks at the Landsat project that are making this talk possible. I'll start sharing slides here, and thanks to everybody again for taking the time to be here. Okay, that's full screen. All right. So we're living in a terrific age, especially for people that use remote sensing data. And that's in part because there's a terrific understanding across many parts of the globe how important this data is, and the investments are being made in not just the Landsat series, which you see on that first slide, starting way back in the sort of the early space race years, and continuing on today with Landsat 9 launching last September and Landsat Next on the drawing board, but also from partners around the globe putting their own sensors in space and making those data available to help us understand how our planet is changing over time. So that's just a visualization of the data on the right and an acknowledgement that the long-term collaboration between the United States Geological Survey and the National Aeronautics and Space Administration has really proven its value, not just to scientists, but even to ordinary citizens. And I'll touch on some of these things in more detail as we go forward. There's some background material, and then we'll get into some of the research details that Mark Fahnestock and I are working on up in Northeast Greenland. So just to further visualize the different satellites and their different sensors that have made this story possible to be shared with you. And I think it's a real testament to this nation, the taxpayers that have footed the bill, not just to put these sensors in orbit, but also starting in 2008 to make all the data in the archive freely available to anyone who can. Well, yeah, they have to navigate the USGS interface or some other version of it, but you know, it's a great gift. It really is. And I'd also like to acknowledge all the engineers and ground support people who not only keep the satellites functioning on orbit, but make those data go through the network and become accessible at the USGS Aeros Data Center out in South Dakota. So that's the timeline. And these are some of the key people that got all of this going. USGS is part of the Department of the Interior, and the Secretary of the Interior at that time was persuaded by the director of the U.S. Geological Survey to launch Project ARROS, basically using the kinds of technology that were being used in the space race to look back at Earth and to transition from the early film photography around the Earth to the robust digital data that became the foundation of the Landsat mission. You know, it's impressive to think about people who are able to understand what is needed and how to get it going, you know, way before the fruits of their labors would become apparent. I mean, it's a tremendous legacy. The legacy had a bit of a challenging start. There were attempts to use sort of existing technology to save money, and so a Nimbus type satellite, weather satellite, was brought to Goddard, and I think the high capacity centrifuge is still over on the main campus, and we tested the model and we broke it. But you have to appreciate, you know, that this was, you know, groundbreaking work, and so it isn't all that surprising that the early steps were a bit faltering, but ultimately successful. 23 July, Vandenberg then Air Force Base in Lompoc, California, was also the site of the Landsat 9 launch in September. So it's always impressive to see a launch. There is a little bit of launch footage in that documentary that's archived and accessible from the National Archive. But it was definitely, again, people figuring out that this needed to be done and they were going to get it done somehow. And so that includes putting a experimental sensor alongside a quote unquote proven sensor. The early weather satellites basically carried a TV camera like instrument. In this case, it was called the Return Beam Vidicon, and it really didn't work that well. But Virginia Norwood led a team that put the experimental multispectral scanner system together and got it on the platform that was launched. And that became the basis of the digital remote sensing revolution that we call the Landsat program. So I had the pleasure of meeting her at the Landsat 9 launch. MSS, with a few scanline issues, worked really, really well. And there's actually an image slightly north of here over Tulsa, but the geologic texture makes this scene that was acquired in 25 July, a couple days after launch, a little more interesting visually. And the cartographer's comment is very clear. Folks, that's a map. And the USGS has a long history of mapping the Earth. And so this was right in their wheelhouse to take advantage of these data. Taking advantage of these data was not necessarily straightforward. Landsat data was in need of technologies that really were just beginning to be developed. We take them for granted now that we can manage these huge data sets and work with them and visualize them. It was not so straightforward back in the day. There was a lot of work converting these digital data into film images and very large prints because that was what people were used to working with. But in time, Landsat big data became the basis for the term, and had a very large number of successes even before Landsat 8 launched in 2013. Colleagues of mine worked on remapping Antarctica using Landsat 7 data, and developing the mosaic of Antarctica that really started to put the features of that sort of hidden land into context, or for people to really understand. Some of the early maps from the International Polar Years are there's details on the edges, and then there's big blank spaces in the interior. And that applied to places like Alaska and the Amazon as well, until Landsat came along. So you can see some of the highlight reel there, mapping the world, inventories of glaciers, discovering earthquake fault lines, errors in nautical charts. I've even used Landsat images to help identify newly exposed islands in the margins of Antarctica, up near the north end of the Larsen C ice shelf. And if you can see my cursor, that's right up about here. So it's tremendous, and I tip my hat to Paul Lohman and the early science team. I overlapped briefly with Paul at Goddard, and it's amazing what has been accomplished. So for those of you that really like the technical details, the different sensor bands of the various Landsat sensors are shown in numbered boxes against the atmospheric transmission profiles that essentially allow solar radiation to penetrate and to be picked up after it's reflected or emitted, in the case of the thermal bands, back to the Landsat sensor on orbit. So early on, that experimental MSS sensor had sort of limited capacity, but it's amazing what you can still do with it, especially in the polar regions. And we'll see what Landsat Next does with the available technology. But it's pretty amazing what you can do with the succession of Landsat sensors. And of course, it's not just their spectral resolution, which has changed, improved. Also, their sensors' spatial resolution has improved. Native MSS resolution was not 60 meters the way it's presented to you digitally. It's been resampled, but that's okay, because that was still really impressive for its day. And there are, of course, higher resolution sensors, and they tend to cover narrower swaths. So for studying an ice shelf, you kind of need that trade-off between spatial resolution and swath width. And Landsat has managed to make that compromise really work over more than 5 decades now. Again, this is a partnership, and it's impressive the technologies required to get anything into orbit, but not only to get it into orbit, but to keep it working on orbit. I believe that circular building at the upper left is actually where the centrifuge is housed, over on the main campus of Goddard. And there's a nice little illustration of the data banks over on the right-hand side that the USGS manages, and in some cases recovers from some of the early satellite images from Landsat were direct downloaded and stored on tapes, and were not necessarily transmitted back to South Dakota. So there's been a huge data recovery effort over recent years in order to get these data accessible to everyone. So a real partnership, and a really successful partnership. And the ground stations are shown in that visualization. And I got to say, if you haven't seen a satellite launch, put it on your bucket list. It's really impressive, even if it's cloudy like it was for Landsat 9 on September 27th. The safe viewing area was far enough away that basically all I really saw was that spot of light ascending into the clouds. But nonetheless, you can really feel the power needed to achieve orbit and to make this happen. Landsat 9 is essentially an improved copy of Landsat 8 with a few tweaks, and we'll talk about that if we get a chance a little bit later. So here we are, utilizing Landsat data to try to understand what's happening in the Northeast Greenland area. Mark and I got started on this as part of a proposal concept, and once I got into it, I just had to try to tell the story. It's not that we're the only people working on this. This is actually a fairly important research area. Many colleagues around the world have been working on this, going all the way back to the folks at the USGS who were putting together all the satellite atlases of cryospheric areas, glaciers around the world. And we basically thought we could add a new dimension to the story here. And so that's what I'll try to show you here on the slides to come. And of course, Zachariæ is not the only important outlet glacier in Greenland, but it is one of the big ones from the Northeast Greenland ice sheet, which tip of the hat to Mark, was defined back more than 20 years ago. That extends well into the interior and makes its way to the coast as an area of faster flow. So very important to understand what's happening there. But even before there were satellites, and there's some colleagues I know that are working on all these old aerial photographs. This is an oblique view of Zachariæ inland, and then the floating ice shelf ice, cracked and broken in many places and glued together by a little bit of sea ice near Schnauder Island, but flowing out of the interior around the corner and then downward and outward towards some additional islands, which we'll discuss here in just a moment. Like I said, there have been many people that have been studying the margins of Greenland for quite some time. And just imagine the folks in the 1930s flying aerial photography equipment and aircraft with open cockpits. So there's definitely a heroic era in Greenland as well as in Antarctica. But anyway, this just gives you a sense of the texture of the floating ice and the fact that it's basically shifting and breaking as it moves off the land and out to into the Greenland Sea. And so you can get a really good sense of that here from the first combination of Landsat images. I don't always identify the dates of the corner images that are used to fill out a scene, but I think you can see from this 1975 MSS image, the flow as in the previous aerial photography taken near Schnauder Island, that the flow is off the interior of Greenland and out the sea, and forming into big bergs and basically jamming up against these islands, the Danske Ohr and Franske Ohr, in what's called Icy Bay or Iceberg Bay, Jokelbuchten. And so what we have now is sort of a 5-year span between 1975 on the left and 1980 on the right. And although the changes are subtle, you can see that there are some ice losses right down here at the very end of the ice flowing into Jokelbuchten. And one of the things that we were able to do is actually show that those bergs, moving now by 1985 even farther south, we were able to map out about 35 points where we could track an iceberg's shape as it moved southward. And this became the basis of one of the things that Mark and I observed before last AGU. You can see the ice all the way out here is changing. And so this area of flow of ice out of the bay becomes especially important because we noticed by 1995 that there was a big shift. And so when we went back and tracked the icebergs and how they moved, we realized that there was something that happened in 1991 where this grayish sea ice, or in this image from Landsat 5, bluer sea ice, had actually melted out and reduced resistance to flow. And there was a shift of the ice field trapped in these islands towards that opening on against the coast, the western side of Jokelbuchten. You can see that a little bit more clearly here because the sea ice melted out again in that area in 1995. And as the resistance to flow decreases, those icebergs over there get kind of mangled and broken as they bounce against each other. And so you'll see this kind of color and texture on the sea ice, signifying relatively soggy conditions, warm. And this is an area that used to have more persistent sea ice, but it begins to get warmer and warmer and weaker as time goes on. And that leads to the unfortunate time period just before the collapse, where Landsat acquisitions were not, shall we say, as timely as you might want. But I wanted to try to not only show where the ice was in Jokelbuchten, but the conditions of the sea ice and how blue and thus covered in melt ponds and thus very unlikely to be providing much resistance to forward flow. And so by 2001, there's definitely ice pushing up against the Franske Ohr Islands, but just barely. And then in 2002, we see that they get another warm summer. That mottled blue color on the Greenland Sea means that the sea ice is very, very soggy. Ice has continued to flow and flush out along the coast, and the icebergs that remain in place next to Franske Ohr finally give way in the first week of August. Landsat coverage only shows the outer extent. I matched up that Landsat coverage with the equivalent Aqua Modus image, just because it's dramatic how many kilometers of ice have already broken free in about a month. This was a house of cards, literally waiting to break up. The older, bigger bergs that you saw in that oblique aerial photograph are all jumbled together, but the main flow area is just breaking loose. And those bergs are making the turn around Schnauder Island and flowing out into the Greenland Sea. And we're not positive about this, but we think that that sort of condition continued right through the winter of 2002 into 2003. A little bit more bad luck for Landsat in this case. The scan line corrector on the Enhanced Thematic Mapper Plus, or ETM Plus, broke down in May of 2003. And so by the time the summer has come, you start missing data along these scan lines. And so we put together this composite just to make sure that we tried as best as we could to show how far inland the breakup of the Zachariæ Isström's outflow had gone by July of 2003. And you can see it a little bit better in this July 2006 image. The USGS turned Landsat 5 back on with its thematic mapper sensor in the northern hemisphere to kind of compensate for the scanline corrector off failure. So even though there's a lot of sea ice in the Jökulbukten, the big bergs have melt ponds on them, and they're still bouncing around down in the southern end. But the breaking of the Zachariæ front continues. 2006, 2009. The ice shelf remnant that was part of Zachariæ's floating ice is nearly isolated now, with big tabular bergs separating it. It's clear that there's little to no flow from the main glacier discharge out into this portion of Jökulbukten. Unfortunately, Landsat 5 lived about 29 years, but it didn't really get that far into the last the decade before this one. So we had to go back to Landsat 7 here to try to show that the Zachariæ Isström ice shelf remnant is now fully detached by 2012. Probably happened somewhere around 2010. It's a minor part of the story. The big part of the story is that the calving events at the Zachariæ Isström have really started to move inland now towards the main into the main outflow from Zachariæ. And that continues into 2015 with again this back up. Hang on. Sorry about that. The mouse only goes one way, apparently. The dark gray ice surface is indicative of a lot of warming and lower albedo. And by 2015, only a couple of the old big bergs still remain down in the southern end of Jökulbukten. And even by 2018, that number has shrunk, and the ice front retreat of Zachariæ continues inland. You can use some of the topographic features on the side of Lambert Land here to give you a reference point. So it's definitely still warm, and it's definitely still changing. And that gets us to 2021, where we had another one of those years, another one of those summers where there was very little sea ice. And so one of the elements of the story we're trying to tell is the crucial nature of sea ice. And we saw that at the end of the austral summer around Antarctica, where very low sea ice conditions led to a lot of changes of glaciers terminating out in the ocean waters around Antarctica. So there's definitely a real thread to this, and importance of emphasizing it. And for contrast there, I outlined what was the 2002 ice extent versus the 2021 ice extent so that you can get a sense of 3,100 square kilometers with about 300 of it still remaining as a sort of trapped iceberg up there in the Northeast. That makes it kind of a unique research project to perhaps instrument that iceberg to see what the contributions of surface and subsurface melting are doing to that ice shelf remnant. So that's the majority of the story from Landsat from 1975 to 2021. And it's, I think, a powerful one. This emphasizes where we were in 1975 on the left, with Jokabukten filled with shelf ice, thicker icebergs, and a good bit of sea ice holding it all together, gluing it all together. And when that sea ice was lost in both 1991 and especially in the early 2000s, culminating in 2002, the shelf ice just couldn't hold on to its grip on the bordering islands. And we'll come back to that point here in just a moment. But big changes, and dramatically so in just the last 20 years. So just a couple of bullet points. You know, it's amazing what you can do with this freely accessible archive, not just here, but around Antarctica as well. And again, tip of the hat to the people that made it possible, going back to, well, heck, before I was even in middle school, you know, making the decisions, investing in the technologies and the data systems and the support systems needed to help us understand change in the 2020s. That 3,100 square kilometer area is about the urban area of Miami. Just to give it a little perspective, scale is one of the biggest challenges in telling cryospheric stories. Again, big outlet for the Northeast Greenland ice stream, extending well inland. There's a paper coming out in Nature in early November, which is going to detail how far inland these losses have transmitted. You can actually see in comparisons of older imagery to new imagery how much additional bedrock is exposed on the margins of some of these glaciers, large ones and small ones. Mark does a lot of work in Alaska, and it's impressive how much they've changed. The ones in Alaska are a little bit easier to get to. Some chance of bears, of course, but it's amazing what you can see with your own eye if you know how to read the terrain. So with that, I'll jump to some late-breaking results. Mark and I were looking at these data comparisons literally yesterday, and just to highlight how much the front of the Zachariæ ice stream has thinned between a 1978 orthophoto DEM and the Landsat, the ICESat-2 data, laser altimetry data being acquired now. The purple color is at least 50 meters of loss generally, and right down near the grounding zone, there's even more. Mark, I didn't put your color scale in because I noticed that you had this handy loss number right on the same plot. But it's really just an impressive physics experiment to see how the ice has pushed out and begun floating and been forced up against these islands and making these are I think we looked at them last night, and about 20 meters of just a berm of ice. And these features in the interior are actually some sort of push of ice off of the margin of Greenland and out into the bay. So it's a very dynamic environment. And we'll close with some bullet points for discussion. You know, this is meant to encourage the iHARP, the collective work that we're all involved in now. I won't read through these all. This will be recorded so people can come back and think about these things at a later time. And I am having some fun exploring the Landsat archive, as I think you can tell, and also being involved in a little bit of work that's trying to understand the improvements in the OLE-2 sensors on Landsat 9 compared to Landsat 8. Again, emphasizing it's kind of a wonderful time to be a remote sensing scientist with these two very powerful sensors on orbit, in some cases overlapping each other, you know, within an hour of one pass to another, because of how their orbits are arranged. So that's a really cool secondary activity that I've got going on. The changes are dramatic. There have been many researchers working on this area, mentioning Jeremy in particular, because of his early work here. More or less the same authorship is going to come out with the new paper here in November. But for the iHARP group, I just want to emphasize it is crucial to understand the linkage between sea ice, shelf ice, and the interior ice. Very dynamic environment. A lot of data sets are going to be needed to have an integrated story. And then we have the challenge of taking rather unique test areas in the short term to be extended to other areas that maybe are less well defined. And I'll close with this slide in particular because this is the 79 north outlet to the same Northeast Greenland ice stream. And it's showing some signs of change, especially in the Spalta outlet between the mainland and this offshore island. And there's research just now coming out showing that this outlet too is likely to experience a rather dramatic collapse the same way that Zachariæ did. And so this image pair just gives you a sense of the scope and scale of changes that have happened and changes that will happen in the not too distant future. And I'll go back one slide and focus on the bullets and take some questions. Thanks very much for your time.
Thank you so much, Christopher. Nikki, are folks able to unmute and ask questions? And you can also put it in the chat. Yeah, go ahead.
They should be able to unmute and they should be able to put the comments in the chat.
So if folks have questions, you can unmute and feel free to talk or put it in the chat.
Okay, let me know when I need to stop sharing so that I can see anything that might be in the chat. Thank you for the clapping.
Wonderful. I'll keep track of the chat as well.
Okay.
So while folks are putting questions together, maybe I will start with one question around the test area. Nikki, I think folks are not able to unmute, Gianmo said. So maybe you want to...
Give me one second.
Yeah. So in the meantime, I was wondering the test area. So, you know, some of these areas are, you know, remote sensing scientists have in view and they've been studying for a long time. Are there ways by which folks in iHARP can identify certain test areas to start with to study sort of, let's say, change detection over a period of time, as an example?
Well, there's a broad range of possible places to look at these things. Obviously, Mark and I have focused on this area of dramatic change. I am the major outlet glaciers are, of course, the ones that get the news, get the intense focus on them, and it's an even bigger problem in Antarctica, of course, because it's a much larger ice area, and it has many more glaciers discharging into the ocean. That said, there is real value in looking closely at some of the areas that haven't changed much. One of these areas was over in West Antarctica, and there were some big outlet glaciers that had until March of this year had very persistent sea ice up against them. But one bad sea ice year led to a fair amount of change very suddenly. And in other areas, sea ice has reformed in some areas that had seen a good bit of open water area and glacial discharge. And that sea ice firmed up enough to slow down some of the outlet glaciers reaching off of the east side of the Antarctic Peninsula. So it's hard to focus on everything, of course, especially if you're budget limited, time limited, personnel limited, what have you. And so that's where the challenge lies: is what can we take from Zachariæ, for example, or Thwaites ice front changes, and extrapolate to other areas like 79 North, or some of the bigger outlet glaciers in East Antarctica on the other side of the continent from Thwaites. So I'm not sure I'm answering your question, unfortunately, but there's
this was very good guidance. I think at least it gives the students a general sense of where to start as well. There was one other question in the chat. I don't know if I can probably. So Sahara has a question specific for Greenland surface melt. She said, I'm curious, how do we calculate ice melt extent? Is there any standard defined formulae for this, like the one we have for sea ice melt extent given by NSIDC?
The folks down at the University of Georgia, Tom Mote, along with his collaborators at the University of Colorado, have a passive microwave algorithm that allows the area to be calculated on a daily basis, essentially, because there's enough passive microwave coverage that, although the resolution is probably on the order of 25 kilometers, it gives you a really good sense of what the surface melt conditions are on any given day. And this is one of the techniques that we use when, especially in the last decade or so, Greenland has experienced these very unusual, extensive interior melt events during the boreal summer, our northern hemisphere summer. Starting in 2012, the majority of the Greenland ice sheet experienced melt over an extended period, and it even extended all the way up to the top of the ice sheet at more than 3,200 meters in elevation during July of 2012. And I point to this in particular because we put out a press release from NASA calling this unprecedented. And unfortunately, it was not unprecedented even in 2012. The ice sheet had melted up at summit at one point in the 1860s based on ice core evidence. But then the Greenland ice sheet melted again in the summer of 2012. This time over a span of 2 separate days, it was above freezing at the top of the Greenland ice sheet. And then in 2021, there was actually a rain event at the top of the Greenland ice sheet. Again, an extensive surface melt. Neither of those two more recent events covered the vast majority of the Greenland ice sheet. And again, that was also true again this year in August of 2022 with a minor melt event, if you will. But that was accompanied by essentially an atmospheric river of warm air and rain hitting the west coast of the Greenland ice sheet, causing dramatic mass losses late in the summer season. So the geology background you alluded to when you introduced me is very present in my mind. Where we were trained, that the present is the key to the past. And it may be that the present is not that good an indicator of the future, however. And that is where things really start to get into very unsettling circumstances, not just for me as a dad, but as a citizen. And merely watching it in real time just makes it even more powerful, in part due to these amazing sensors that I have only scratched the surface of how many different ways we can look at the polar regions. But I'll stop there and take another question.
That's great. There's actually a few different questions coming in, and I'll just jump onto the one that's related to your last comment. It's from Nick Halsey, from one of our collaborators in iHARP. He said, thanks for the interesting talk. Do you mostly think the utility of Landsat 9 is in continuing the time series, or is there anything about its instrument suite that creates the potential for novel science?
Actually, both Landsat 8 and Landsat 9 have a kind of untapped power in their thermal bands. Landsat 8 had a little challenge with one of the two thermal bands. Landsat 9 fixed that, and some of my colleagues are working on really taking advantage of the ability to get a pretty darn detailed 100-meter resolution. It's in the data, it's resampled to 30 meters to map the rest of the bands on OLI and OLI 2, but at 100-meter temperature data is one of the other ways that we can begin to explore what is the surface temperature of Greenland, what is the surface temperature of an individual outlet glacier over time, what is the temperature of the waters right off the front of one of these retreating glaciers. When there's open water, the thermal bands will give you a quantifiable measure of the surface temperatures. And we know from some of the research that those colleagues are doing that there's flow of water from offshore up into some of these deep channels and reaching up underneath the floating fronts and eroding them thermally. And so that meltwater can be traced when conditions are right, and help us better understand let's put it this way, a very difficult to research environment. The waters at the front of a glacier are full of big calving icebergs. They tend to drag off buoys and sensors that are placed even at some depths. And so having a way of safely sensing what's going on is, I think, one of the ways that Landsat 8 and the improved thermal bands on Landsat 9 will really add to the story that we're trying to understand here and elsewhere in the polar regions.
Thank you so much. One question from our student Imam. Thank you for your presentation. When you calculated sea ice melting, did you also consider the loss of sea ice thickness?
That is harder to do. It's one of the reasons that the ISAT-2 mission was launched with a very high latitude orbit, basically covering from 88 north to 88 south, was to try to better understand thickness changes over these areas of frozen seawater, sometimes with considerable amounts of snow on top of them, and how they're changing in particular areas. For the recent sea ice minimum around Antarctica, that was a combination of visual sensors and passive microwave sensors. I don't know that anybody has been able to put all the ISAT-2 laser altimetry data together to show a dramatic thickness change. But when sea ice blows out, it can blow out extremely quickly in the austral summer and also the northern hemisphere summer, the boreal summer. And so the integrity of sea ice is increasingly a question, as it is known to be thinning and becoming more and more younger sea ice, not multi-year, maybe a year or two, and thus not very thick. And so that has real consequences for incoming solar radiation, and for the ability of storms to disrupt the sea ice cover in these polar regions, because it's inherently thinner and weaker. So this is another dynamic area that is not my specialty, but there are a number of researchers working on that at various institutions around the world. The sea ice changes in some ways are more dramatic in the past 50 years than even some of the land ice changes. So I'll stop there.
That's great. Another question from Professor Jianwu Wang. What are the relationships between ISAT and Landsat?
Well, they're inherently different sensors, in part because Landsat is a passive sensor. It takes in energy that's coming up to it, whereas ISAT, the original mission from 2003 to 2009, and the ISAT-2 follow-on, launching in 2018, emit laser energy in very specific frequencies and wait for that energy to be reflected back into the orbiting telescope. By knowing the timing on when you sent the energy out and where you were pointing, especially important because orbits do wobble, and then knowing where you are and what time it was very precisely when that energy comes back to the telescope gives you the satellite range. And so you can calculate relative to the ellipsoid and then do a geoid correction, and you can get very precise elevations from those returned energy packets sent out by the laser altimeters. More or less the same phenomenon with the Cryosat-2 radar altimeter, although the radar pulses tend to be broader and can be sort of reflected from the highest topography in the pulse area rather than the more precise footprints from the laser altimetry. But they both essentially give you the topography below, and especially if you accumulate enough data, how the topography below is changing. And that applies to forested areas as well as ice areas. Landsat takes advantage of some very, very dramatic improvements in GPS location technology on orbit. So the early set of Landsat sensors were more or less The scenes that were returned were processed and positioned based on sort of established knowledge of what the topography was. And we've discovered as we've transitioned in Landsat from collection 1, which used sort of less evolved image calibration and validation techniques, to collection 2, which has enhanced the whole series of satellites. But you can really see the dramatic improvement with Landsat 7, 8, and 9 in knowing where the sensor was and where it was looking very precisely. And those data are extremely valuable for deriving something, especially in the cryosphere, basically ice velocities by not just having a single look, but having multiple looks of these areas. You can see those features on the surface that you saw in some of the images that I showed. You can see how they move with time. And that allows you to, and Mark showed some of this as we were talking yesterday, you can actually see seasonal variations in flow speed. ISAT-2 will give us seasonal variations in ice elevation in these big glacial outlets, but Landsat and other sensors similar to it, Sentinel-2 for one, and their radar sensor, Sentinel-1 sensors, also can give us a sense of motion over time, and that really adds to the dynamic understanding of these big outlet glaciers. And even slower moving portions of the ice still have their story to tell. This has been documented in the people looking at subglacial hydrologic systems, where the ice actually inflates and deflates as water is pumped through the system. And one of the exciting things that we're just looking into now is the fact that because Landsat 8 and Landsat 9 can overlap their coverage with very short time intervals, is we're now looking to see whether we can see changes in shadowing as some of these hydrologic systems change during the course of a summer season. So stand by for more on that.
That's great. I know we are getting close, but there's a couple of other questions that I can combine into one question, Chris. Are you okay with one more? Okay. So a couple of questions around the data itself. What is the effect of coordinates when taking images of icebed map, missing data that happens in the radar images? And related to that, are there regional divisions defined in Greenland, like Pan-Arctic region? Are there any regions of interest?
That may be beyond my capability to fully answer, but I know that everybody at UMBC can easily find my email. So if anybody wants to follow up with some specifics, I can take a stab at it, or we can open it up to the group to try to contribute to that, as we're about close to the end of the hour. So rather than me hazard a guess, maybe this one can we can discuss it in a follow-up.
That sounds great. And I think we can share your email address with the iHARP folks who put the questions in the chat. There's a bunch of interest and a lot of good questions coming in. So I want to be respectful of everybody's time. And with that, I want to really thank Dr. Shuman for a very engaging talk. And I'm sure you'll have lots of follow-up requests for information and other things coming along your way. Thank you so much.
Thank you for inviting me, and for everybody taking the time to be here.
Thank you.